Hello, my name is Gianluca Tabella, and I'm a Brute 21 PhD candidate at NTNU. I'm here to present to you my research in data fusion for high-performance leak detection. In the offshore oil and gas industry, oil spills and gas dispersions are extremely critical events. Leaks pose a threat to the worker's safety, the environment, and the equipment that is present in the area of interest. For these reasons, an efficient detection system needs to be both accurate and fast. Accurate, as we want to avoid dangerous misdetections, without increasing the number of false alarms. And fast, as we need our detection system to be able to recognize the leak rapidly without affecting the system's accuracy. Most common monitoring systems employed nowadays rely on a set of independent sensors. In these cases, each sensor triggers an alarm that is sent to the control room. However, the different sensors might contradict each other, with some sensors sending an alarm and some that do not. The lack of a proper optimization when it comes to handling these inputs is exactly what inspired this research. The main idea is to have a central unit called Fusion Center, whose task is to collect and process all the inputs coming from the sensors. The Fusion Center can take advantage of high processing power as well as the possibility of taking into account physical models and past inputs. The intent of such a network architecture is to create an intermediate layer between the sensors and the control room that can facilitate the decision-making process by employing state-of-the-art data fusion techniques. But let us take an example. The Goliath FPSO is a production platform located in the Barents Sea. This platform uses a subsea production system for its operations, where each template has its manifold monitored by 3 hydrophones as part of the leak detection system. So for this application, we designed what we call a Bayesian sequential fusion architecture. In here, each sensor measures the sound in the surroundings of the manifold, and in case it detects a leak, sends an alarm to the Fusion Center. In our proposed architecture, the Fusion Center fuses the inputs coming from the sensors by taking advantage of the specification of the sensors, the acoustic model of the leak, the past inputs sent by the sensors, the age of the components, and the components' updated failure rates. Now, let's compare our proposed system with a different system performing data fusion, but that lacks the main features of our sequential Bayesian fusion architecture. For this comparison, we simulated the lifetime of the Goliath platform with 2 leaks occurring. The more traditional architecture was able to quickly detect the leaks. However, we can see that we also registered 8 false alarms. Now, let's have a look at the same simulation by using our proposed data fusion strategy. We can see that we were still able to quickly detect both leaks, but we were able to do so without a single false alarm. This design strategy is not just limited to subsea oil spills. A wide range of applications is available, including hazardous gas detection and fire alarm systems. An example is our last work where the aim was to design a system able to detect carbon dioxide dispersions. For this work, we've designed a data fusion strategy where the Fusion Center can take advantage of real-time meteorological data such as temperature, wind speed, and wind direction. With the results of this research, we were able to produce a promising number of publications in both scientific journals and academic conferences.